Again, keeping in mind that this is an introduction that I'm giving through short podcast, so you have to read up depending on your comfort with the math. I'm hoping to just explain the physics with the math in the background, but you should read up the details, keeping in mind that this is one model that Bin Wang is using to go through the dynamics. So we looked at this and said we need a minimum of 2 layers for doing MJO because there is a baroclinic mode and there is a barotropic mode. So in this 1.5 layer model, we looked at the gravest baroclinic mode and the higher modes, and depending on the assumption you make about the heating and so on, the barotropic mode may be much smaller than the baroclinic mode, at least the gravest mode, and can be ignored. Or in the real full MJO dynamics, it turns out that the barotropic mode cannot be neglected. So if you don't know what is barotropic and baroclinic, definitely you have to read up, but in a simple sense, barotropic mode is also called the external mode. So you can think of it as being uniform in the whole column and very fast moving waves, and under certain circumstances they can be ignored depending on the simplification you are making. And baroclinic modes are known as the internal modes. You can also mathematically see it as the gradient of pressure and gradient of density. If the cross product grad P cross grad rho is 0, then it's a barotropic system, which means the isopycnal lines and the isobars are parallel to each other, which has all sorts of consequences in the real flow. Here, several types of heatings are included in the equations. So we have, let me do the pointer. So you have the heating coefficient due to wave convergence, which would give us the wave cisc that we talked about before, convective instability of the second kind caused by the wave convergence leading to instabilities able to drive waves and the growing modes. There is a heating coefficient due to frictional convergence, which we will discuss a little bit more here and in the next podcast. And of course there is heating coefficient associated with evaporation, the enthalpy flux coming into the atmosphere from the surface. So using the 1.5 layer model, we can generate the low frequency waves involved in the MJOs to look at the dynamics. So here it's the heating is neglected, so you have the boundary layer and the free troposphere, and the convergence friction in the boundary layer always there. Boundary layer means frictional layer. That's going to give you an Ekman pumping from the background flow, which is able to generate waves in the free troposphere without any heating. So it's the baroclinic adiabatic flow in the free atmosphere, and it generates the Kelvin wave here, which is you are looking here at the axis, which is the zonal phase in degrees. So you can think of it as longitudinal direction, and this is the non-dimensional meridional direction. And the Kelvin waves are trapped to the equator very tightly because it is related to the Coriolis, and the equator is like a dynamic boundary. It's a gravity wave, so the restoring force is you can think of as a gravity with the perturbation coming here, let's say from the Ekman pumping, and you generate equatorial Rossby waves with their off-equatorial geopotential height anomalies. So these are geopotentials, and again you have tightly bound to the equator in the Rossby wave structure as well. And the MJOs have a very large zonal scale compared to the meridional scale. This amounts to having nearly geostrophic or geostrophic balance in the free troposphere where there is no friction, and that also filters out the waves like inertia gravity waves and so on, so that you get the long wave approximation which gives you geostrophic balance off the equator, of course, because if you know geostrophic balance, it has Coriolis in it, which goes to 0 on the equator. So geostrophy becomes a strong constraint of the equator. Associated vertical pressure velocities here, you can see there is a consistent vertical flow associated with the Kelvin and Rossby waves, and the impact of the friction is that the waves are slowed down a little, and the Rossby wave vertical pressure vertical velocity structure is tilted, as you can see here, compared to the free waves. And there is a phase lag between the pressures and the vertical velocities, which with respect to the easterlies and the westerlies. So you have easterlies and westerlies associated with these geopotential height anomalies of the waves, and that displacement between the pressure and the vertical pressure velocity becomes critical for the eastward propagation as well. So this model obviously wants to emphasize frictional convergence. Here explicitly looking at the behavior of the frictional convergence instability mode associated with the MJO model. Here growth rates and zonal phase speeds as functions of wavelength and maximum SST on the equator are shown. So sea surface temperature is critical in the frictional convergence because that's going to determine your enthalpy flux and the instability that you can drive in the troposphere above the boundary layer. Normalized upward motion at the top of the boundary layer is computed here. Computed for the growing FCI mode under SST of 29.5 degrees centigrade. So some SST where instabilities are growing is chosen to show the vertical velocities, upward motion, and the example is shown from observed winds and convergence to argue that the model has a realistic representation. So here, if you look at wavelengths and SSTs, for any given wavelength, as SSTs warm up, you begin to get unstable growing modes, which is what you want for MJO, which is a unstable mode, and that's why it's propagating and oscillating. And the higher wavelengths can get unstable at lower SSTs. You are talking about a degree here. So higher SSTs can generate instabilities at shorter wavelengths, and the phase speed decreases as the wavelength increases. As the wavelength increases, the phase speed decreases. So planetary waves are moving slower, and the higher modes are propagating faster. Associated with them, again, you get the upward motion at the top of the boundary layer, which is what is going to drive the instabilities in the free troposphere. So I hope it's clear how the boundary layer processes are being coupled to the troposphere, which is where we are always looking for MJO dynamics. Okay, so you can read it up if it's not clear, but in this short introduction I'm going to just introduce the basic concepts. And from the observations, we are looking at observed winds and convergence. So when you have convergence, which is the negative contours here, you have the clear convergence, and when you have divergence, you have winds showing divergence away from the center of the divergence, and you have other wave structures there as well. Of course, these are filtered observed winds and convergences and not the totals. So the argument here is that the frictional convergence instability can explain the tilted structures. So the MJOs have Kelvin waves and Rossby waves, and yet it picks the eastward propagation, which has to be explained. And as it's propagating eastward, the vertical structure is tilted backward, which in this argument frictional instability is critical for that, because the wave convergence heating in this model is very weak, so the wave CISC that we talked about doesn't work. So frictional convergence instability is invoked, and this frictional coupling is also able to explain the slower propagation speeds. Okay, so obviously the model wants to build on frictional convergence instability as the core paradigm. So it explains, it is built basically to argue that frictional convergence instability is very critical. And as I said before, this is not the only model, and not all models agree that the frictional convergence and pumping of moisture from the boundary layer into the free troposphere is very important for MJOs. There are other models which claim free tropospheric moisture convergence as well for driving the instabilities. So again, you have observations of MJO at various spatial and temporal scales, and you are using the data to fit the models, and then you are testing the models back against the data like we showed here with winds and convergence. And often you're also going back to GCMs and seeing how the GCMs are doing the MJO in them when they do a good representation of MJO. Okay, so it's kind of the way science works: data, hypothesis, more data, theory, models, and then validation and confirmation. And again, we have multiple models, which means there is no consensus, even though we know all the fundamental processes that are important for MJOs. Okay.